Hi everyone. So as you see, when we move from a monolithic architecture to microservices one, there is actually a big change of paradigm. Instead of just calling local methods, the services now start to talk to each other through the network. And today, let's dive in and take a look at the synchronous communication model in microservices architecture. So, to minimize the disadvantages of network communication, it is very important to follow the criteria of a good communication protocol. These criteria work like kind of map that help us evaluate and compare different approaches. Let's look at each of them in more detail. Backward compatibility. This means that the protocol should make sure that updating the API of one microservice will not break the communication with another microservices that use it. For example, if microservice A updates its API and releases a new version, the communication with microservice B should still work. Technology independence. A good protocol should not limit us to specific technologies, like programming languages or frameworks. This is one of the key advantages of microservices architecture because it allows each team to choose the best tools for their tasks. Simplicity for clients. The protocol should be as easy as possible for those who will use it. If integration or using a microservice requires too much effort, the clients, other microservices, or external systems simply will not want to work with it. Explicit interface. The protocol should provide a clear and easy to understand interface. This helps developers quickly see which methods are available, what parameters they accept, and what data types are returned. It really simplifies both development and integration. Closed implementation. Ideally, a client should just be able to import a library, call the needed method, and get the result without going deep into the hidden details of how the network communication or other processes work. This way, developers can focus on business logic instead of low-level technical stuff. So, let's talk a bit about synchronous communication. You'll see the most common pattern here is request response. And basically, it means that the execution thread is blocked until the client gets the answer. In simple words, the thread just waits and continue working until the server sends something back. If the request cannot be handled right away, well, it is considered an error. For example, the order service called the payment service to process a payment, and we block until the payment service finishes its job and only then gives us the response. Now, what are the advantages of this model? First, monitoring is simple because you have a clear time frame, start and finish of the request, and you can even track it in normal logs. Second, it is great for real-time scenarios where you really need the answer immediately. But the thing is, synchronous communication still does not fix the problem of lost requests. They can still happen, and not only because of heavy load. And finally, when we look at today's world, the typical technologies we see for service-to-service communication are SOAP, REST, GraphQL, and RPC. Now, this is one of the so-called heavy communication protocols. And one of the reasons why it feels so heavy is because it uses large XML messages. That makes the interaction slow and also very big in size. What's more, SOAP does not only work over HTTP, it can also use SMTP, TCP, and other transport channels. And the key thing is that SOAP always defines a very strict contract with VSDL. You can think of it like a signed agreement about the exact format and behavior of the API. But when we compare SOAP with modern, more lightweight protocols that are popular in microservices today, it often looks like something from the past, too complex and too heavy. Still, the truth is many companies continue to use it, especially banks and financial institutions. So let's move on to representational state transfer, or simply REST. This is not a protocol but a concept. The idea is that the server gives the client access to data in the form of resources. And here is something important. Even though REST is usually connected with HTTP, the concept itself does not require it. You can use REST-style communication even with simply text messages by adding keys, headers, and sending data in JSON. You could even do it over Kafka if you really wanted. Now, REST over HTTP is usually based on four main operations, known as CRUD: create, read, update, and delete. They map directly to HTTP methods: post, get, put or patch, and delete. Resources are often encoded in the URL, including IDs and related entities. For example, you could have user ID and payment ID inside a path like /users, user ID, /payment, /payment ID. But here comes a problem, something called a security breach. Imagine a client sends the user ID of one user, but then adds a payment ID that does not belong to this user. In that case, the system might return someone else's payment data. And the truth is, this kind of security issue happens quite often in practice. So it's really important to keep it in mind when designing an API. Now, there is something called the Richardson Maturity Model, which describes the levels of maturity of a REST API. Basically, it shows how a REST API can grow, starting from the simplest forms of interaction and moving to more complex ones. So let's go through them. Zero level is the most basic one. Here we just use simple HTTP interaction with requests. In fact, all action goes through a single URI. At first level, we add the idea of resources. This means we can identify data with URLs. For example, /employee data /2132 can be used to get information about a specific employee. Moving on second level, introduce the use of standard HTTP methods. So now we have get for reading, post for creating, put or patch for updating, and delete for removing resources. At this level, we can also filter data using get parameters. And then we reach the highest level, third level. This one adds hyperlink for navigation between resources. So instead of only returning IDs, the API gives the client ready-made URLs for the next actions. For example, a link to the next page when we use pagination. But here's the thing, in real life, most REST APIs stop at second level. They use HTTP methods and resources, but not hypermedia links. And that's because third level, especially the head OAuth concept, is often complex and not always justified from a business point of view. Alright, so let's take a look at the pros and cons of using REST. Pros: wide adoption and intuitive use. REST is one of the most common solutions for synchronous communication, and almost every developer has worked with it. This makes it very recognizable and relatively easy to learn. Simply for client. REST APIs are quite easy for clients to use, especially at second level of the Richardson model, which covers most real implementations. It allows developers to work with standard HTTP methods and resources. Use of HTTP methods and resources. REST makes strong use of standard HTTP methods like get, post, put, delete, and the idea of resources, which makes building APIs very intuitive. And now the cons. Weaker performance. One of the biggest complaints is performance issue. Since data is usually transferred as JSON or plain text, it's not very efficient when we deal with large amounts of information. No schema by default. REST does not have a built-in schema. Without extra tools like OpenAPI, it's hard to automatically validate the structure of requests and responses. No real backward compatibility. REST doesn't guarantee backward compatibility. If you change the JSON response structure, the client either understands the new structure or it breaks. And this happens a lot. Hard to keep documentation up to date. Documentation for REST APIs quickly gets outdated because the protocol does not document it itself automatically. This means it must be updated manually all the time. Diversity of implementations. In practice, everyone implements REST in their own way, which means there are no strict standards. APIs often become a kind of dump where people add anything they want. This requires constant control through code reviews and contract discussions. So GraphQL solves many of the problems that REST has. The main idea is simple. The server clearly describes the data types it provides, it implements methods to work with them, and then it generates a schema that is shared with the clients. Thanks to the schema, the client always knows exactly what information they can request. Now let's highlight the advantages of GraphQL. Speed. Clients can ask for only the data they really need, which avoids sending too much extra information. This often makes it faster than traditional REST APIs, where the server usually returns a fixed set of data. Auto documentation. A GraphQL server can describe its own schema, so developers can easily see what types, fields, and operations are available. Great for microservices. It works really well with a microservices architecture, especially for the backend for frontend pattern. The frontend can talk to a single GraphQL entry point, which then collects data from many microservices and hides this complexity from the client. Strict typing. It enforces strong typing of data, which makes the system more reliable and the interaction between client and server more predictable. But of course, GraphQL also has its downsides. Requires learning. Developers need to learn a new query language and new concepts. Performance issues. It can run into performance problems, especially when queries require merging data from many sources, or when the queries are very deep and complex. Complex caching. Caching in GraphQL is harder compared to REST because the queries are flexible and can vary a lot. Exposes internal data model. GraphQL can reveal parts of the server's internal data model, especially when frameworks automap database tables to GraphQL types. This can raise security concerns. Okay, one of the key strengths of GraphQL is that it lets the client get only the data it really needs. This flexibility comes from the fact that the server defines a clear data schema. On the slide, we can see an example of a GraphQL schema with a type called transaction. It has different fields like ID, amount, status, and updated at. The server describes these types, implement methods to work with them, for example, update transaction status and get transaction, and then generates a schema that is shared with the clients. When the client sends a query, it can ask exactly for the fields it needs without getting any extra information. For instance, in the query update transaction status, the client asks to update the status and only return ID, status, and updated at. And in the response, we receive exactly these fields without the amount. This way, GraphQL helps us avoid sending unnecessary data. Now, I also want to tell you about Apollo Federation, a solution that let us combine several graphs from different servers into what we call a supergraph. And this is especially useful in microservices. Imagine a situation where you have several microservices and each one has its own API, maybe even using different protocols. For example, one service works with GraphQL, another with REST. Normally, the front-end application would need to know about each of these microservices and their protocols. But with Apollo Federation, you can create a single entry point. The client talks only to this supergraph, which lives on the Apollo Federation gateway. The gateway already knows how to get and combine the data from all connected subgraphs. This approach works perfectly with the backend for frontend pattern. The frontend communicates with just one server, and that server aggregates the data from all the different microservices behind the scenes. Good. Let's move to remote procedure call, or simply RPC. This is a concept that allows the client to call remote procedures on another server as if they were local methods. The main idea was to hide the complexity of the network as much as possible, so that engineers could focus on business logic without worrying too much about network details. RPC usually has an explicit schema, its own network protocol, and also uses efficient serialization protocols. But of course, RPC also comes with some downsides. It is often tightly bound to specific technologies. It usually doesn't guarantee idempotency, and debugging RPC calls can be difficult because the data is often sent in serialized binary format, which makes it hard to simply read and analyze. Now we'll talk about common technologies for implementing RPC. The main ones are gRPC, Thrift, and Avro. These frameworks give us the tools to call remote procedures almost like local ones, and that's really the core idea of RPC. gRPC developed by Google in 2016. It's considered the de facto standard for RPC today. For data serialization, gRPC uses protobuf. This means you describe an explicit schema in protofiles, and then interfaces and classes are automatically generated in different programming languages. gRPC works on top of HTTP2. It supports both synchronous and asynchronous communication, as well as streaming, which lets you send data in chunks without closing the connection. That's why gRPC is widely used by big companies like Google, Uber, Netflix, Spotify, and Dropbox. Overall, a data serialization and RPC technology that was created in the Apache Hadoop project with the first release back in 2009. Overall, it's especially good for serializing messages in Kafka and is widely used together with Hadoop. And the last one, Thrift, a binary communication protocol created by Facebook in 2007 and later moved to Apache Foundation in 2020. Thrift also supports automatic code generation for many programming languages and is used in companies like Facebook, Twitter, Quora, and Pinterest. So, even though these technologies are different in detail, their common goal is the same: to provide efficient, strongly typed, and high performance communication between services in distributed systems. On this slide, we can see an example of a schema, a request, and the response we get back. If you want to know more about how to describe schemas and methods, you can always check the official website of the technology. So let's quickly summarize. Today we talk about how communication changes when we move to microservices. Instead of local calls, we now work over the network. We define the main criteria of a good communication protocol: backward compatibility, technology independence, simplicity for clients, a clear interface, and hiding implementation details. We discuss the synchronous request response model, its advantages for real time scenarios, and typical implementations like SOAP, REST, GraphQL, and RPC. We look deeper into REST and the Richardson maturity model, and we saw both its strengths and its weaknesses. Then we talk about GraphQL, which let the client request exactly the data it needs. And finally, we touch on RPC and gRPC, which bring strict schemas, efficient serialization, and high performance for service-to-service communication. Okay, here is a small quiz if you would like to try it. And here my social media. And thank you very much for your time and attention. See you. Bye bye.